He is a PhD candidate in this program. He's also a research associate at the Lawrence Berkeley National Lab. His research interest lies in energy and transportation systems engineering, and the title of his thesis is The Value Proposition of Vehicle Grid Integration, and he is advised by Professor Alexei Plotnikov. So let's give him a warm welcome.
Thanks. It's actually the title of this talk. The thesis is a little bit different. Okay, so I've been thinking a lot about electric vehicles and about the grid and about coupling between the two. And so this talk covers really the heart of my dissertation, which is thinking about what kind of value electric vehicles could bring the grid by supplying flexibility to the grid. Because as I'll explain, as renewables come onto the grid, they require that we also add flexibility to match them so that we can keep the supply-demand balance in check. So I'm going to do an introduction and then look into the, or sort of state the problem as I see it, and the scope of what I'm covering in this study that I'm mostly focusing on. And then there are really two key components to the overall work. So one is developing the model of plug-in electric vehicles and their charging demand, and this is using an agent-based approach. And then the second step is then coupling that model to a model of the electric grid, and then using that as our basis for trying to assess this value of this flexibility. And I want to point out, this is my acknowledgement section. All these people contributed to this work. It wasn't just me doing this, and they all provided very valuable contributions, with a special call out to Rashid Warwick and Julia Zainai, who both substantially contributed to those two sections. Okay, so in short, the transportation sector in 2016 overcame the electric power sector as the leading sector in the US economy for greenhouse gas emissions. And what's worse, we're on an upward trajectory in transportation, whereas electricity and industry are on a downward trajectory. And transportation is a very tough nut to crack in terms of reducing greenhouse gas emissions, because we have all these varied sources all over the place, and each of those are coupled to people who have very strong feelings about their mobility and their vehicles. But, and I should say, there are many different approaches to reducing greenhouse gas emissions from the transportation sector. Electrification is one of those approaches, but this is not to say it's the only approach. Meanwhile, though, electrification in the transportation sector is happening. It's been growing at exponential rates for the last 8 years, and most of this growth in the early years was driven by policy. There have been substantial subsidies in most of the key markets around the world in order to get these out to the market. But the cost of batteries are coming down, and batteries are the big the big ticket item in the electric vehicles that historically have made them more expensive than conventional vehicles. But as the cost of batteries come down and as the energy density of these batteries go up, we can have longer range vehicles that are competitive in terms of sticker price with conventional vehicles. And we're, depending on the vehicle, we're actually getting to that point right now. So this should help to allow these to sort of enter the market on their own, as opposed to being driven by policy. Okay, meanwhile, on the grid side, renewables are really hitting a breakthrough point right now. Like, we are right in the middle of the beginning of a major change in where our energy comes from in the electricity sector. Renewables globally have already overtaken natural gas, and a decade from now they could overtake coal in terms of the total amount of electricity that's produced annually. And this is largely being driven, well, it's a similar story, right? Over the last 10, 20 years, it's been driven by policy. Governments have been aggressively incentivizing the installation of renewable energy, but we are now hitting this price point where without any subsidy, depending on where you are, solar and wind are cost competitive to natural gas and coal. And we're seeing that even coupling solar with battery storage on the grid can be cost competitive to existing incumbent technologies. So major transformations on the grid, but there's this problem where we're putting this new source of generation that's non-dispatchable this requires we add flexibility to the grid. And we can get flexibility in multiple ways. So we can add storage, we can add more generation than we need and hold some of it back in reserve so that we can turn it up when we need it. We can actually enhance flexibility by allowing there to be greater amounts of imports and exports between regions. We can improve transmission between regions, and then we can do demand response. And so EV flexibility is a subcategory of demand response. And really the big question I'm focusing on is how much flexibility is there in EV charging and how valuable is that flexibility to the grid? And really where this leads me is, given how valuable is it, how likely is it that this is going to be something that will actually play an important role in the future? So this is the question that I'm trying to answer. Okay, in order to do this, we want to model EVs, we want to model the grid, and we want to somehow link them together. So in general, modeling EVs has some challenges compared to, say, traditional, say, travel demand modeling, because you have to think about the fuel, right? You have to worry about the fuel. So EVs are still range limited and charging is slow. If you compare just the delivery of energy from the socket to the battery to the delivery of energy from the gas pump to your fuel tank, we are talking orders of magnitude different. Thousands of times slower to charge an EV. A trip-based analysis, so if we just have origin destinations derived, say, from cellular data, or if we just have ODs from a 4-step travel demand model, it doesn't really help us because the problem isn't so much about whether we can drive an EV on one trip, it's more about whether we can drive it on the multiple trips over a day or over multiple days. So you have to track that state of charge from trip to trip. You have to think about where the vehicle is in between because that's your opportunity to charge it. And then human behavior plays a pretty prominent role in how EVs are charged, when and where. And then of course when we start thinking about where this energy is coming from, the grid is fantastically complex, so that introduces its own constraints and complexities around trying to answer this question. Okay, so these are some typical simplifying assumptions that people make in the literature when they are modeling EVs, and there are, these assumptions are totally appropriate depending on what you're trying to do, how you're trying to do it, and there's a pretty good reason why people typically don't go beyond these assumptions, which is because it introduces a lot of complexity, it takes a lot of time to sort of endogenize these things. So assuming charging infrastructure is unlimited, this is very common. That in models, EVs just go wherever and then they just charge. But anyone who may own an EV probably can tell you that this is just not the case, and I would argue it will never be the case, or it's unlikely to be the case. Ignoring the spatial dimension to charging infrastructure is common, and it's something that I've done. Ignoring human behavior, and then on the grid-connected vehicle side, assuming EVs are price takers in the electric system. So this just means that price is like an exogenous input. But if we're talking about large penetrations of EVs, you actually are increasing load to the extent so much that you're actually changing the price, the electricity that's delivered. Using today as a proxy for the future doesn't work well, especially with the grid because it's changing so fast. And then ignoring competing sources of grid flexibility is a common assumption because then you have to think about storage and about other types of flexibility. And so we've made an attempt to move beyond all of these assumptions in our work. The way we're doing this on the mobility and charging side is using agent-based modeling. We've taken the MatSim model and we've extended it to represent the sort of detailed interactions of EV drivers engaging with charging infrastructure. So in agent-based modeling, in general, just sort of the ABCs of it, you create a virtual environment, you populate it with agents that have a set of rules by which they operate, you observe what happens, and what's nice about it is you have this sort of complete omniscience over everything happening in the system. What's also nice about it is you can look at these rule sets for these agents and just use, for the most part, you can use common sense as to how these agents behave, what they do. It's all very small and micro, so it's approachable. But then you put them in the system and things happen and you have to, it's similar to interacting with the real world with data, right? You have to think about why is that happening. You have to set up experiments with your model in order to drill down and understand what are the mechanisms that are driving your results. So by taking this approach and learning about the system this way, you almost learn through the modeling process more than you learn from just looking at a final result at the end. So here's a visualization of what's happening in the model. There's a person driving an EV. They arrive at their destination. They do a search in the vicinity for available chargers, and they go through a choice process about whether or not they're going to charge, and if they do charge, which charger they're going to use. Then they plug in. We're representing the infrastructure in a detailed way, different types of chargers, as well as the number of parking spaces that are accessible to those chargers. And then we're doing this for the whole SF Bay area. We're driving this model with activity data that came from the Smart Bay team. And then we can take this result and summarize and sort of use the information that comes out of the model to answer the questions we're interested in. So we're doing our best to drive the model with realistic data. We had access to vehicle make and model by zip code based on pulled data. We have, I already mentioned where the activity chains came from. We're sort of assigning the BEVs and PHEVs to the population based on a heuristic which basically says that if you're driving an all-electric vehicle, you're unlikely, and it only has 70 miles of range, you're unlikely to attempt that if you're driving 200 miles that day. So instead we would assign you a plug-in hybrid electric vehicle, and I'm realizing I forgot to mention what the difference is. This is all-electric vehicles. These are hybrids, which have an extended EV range. Okay, and then the congestion data came from Smart Bay, and we are only modeling EVs in this work. And so basically these EVs are congestion takers, not congestion makers. Here's our charging infrastructure assumptions. We assume everybody has a charger at home, and there were 68,000 EVs in the model, and that's why we get 68,000 here. This is a pretty weak assumption, though. We assumed everyone had a level 2 charger, which is faster than just plugging into your outlet. We probably should have assumed a distribution over that. Okay, we did a calibration where we tweaked the intercepts of this choice model in order to get the bulk propensity to charge from our virtual population to match data that we got from a charging infrastructure provider in the Bay Area. So ChargePoint is the leading provider of infrastructure in nationwide, and we were able to get some of their data and do this rough calibration process. Oh, I should mention that the choice model we're using came from the literature. It was done through a survey that was administered at University of Washington, one of Don McKenzie's students, and we kept all of the intercepts in the model as they were from the study, and then we did tweak the we kept all the multipliers, and then we did tweak the intercepts in order to get sort of this bulk utilization to line up. So once we had that calibrated model, we used it in the context of a couple of thought experiments, and we did this in order to kind of test out these typical assumptions that I brought up earlier. So one assumption people will make is abundance of infrastructure. So if we populate the model with abundant infrastructure and run it, we get people charging their vehicles and producing this kind of demand for electricity over the course of a day. But if we use constrained infrastructure, we end up with a very different shape for the demand. And this has important implications if what we're trying to do is understand the interaction between these EVs and the grid and the associated costs. But meanwhile, even in this constrained scenario, we know that there's some latent demand for charging, right? We know that people would charge if they could, but when we look at the chargers that are actually in use, there's a whole bunch of chargers sitting idle. And the reason these chargers are sitting idle is because they're not necessarily located where they're needed. So ignoring space when we're thinking about access to chargers is a fraught assumption to make. And then finally, the behavior also matters quite a bit. So if we take the choice model that we used here and compare it to just a heuristic, which is always charge whenever you arrive if you can, if there's a charger available, or flip a coin and decide whether or not to charge based on a uniform random draw, or sample from this nested logit distribution, we get different charging profiles, although this one and this one are decently close. Okay, so given that we have this model and we can use it to predict these individual charging sessions, what we're going to do next is couple these to a power sector model. And we do this by going through a post-processing step on these charging stations in order to aggregate the load and analyze the flexibility inherent in this load. And then we send that as input into Flexos. Flexos models the dispatch of generation on the grid. And I will talk about that more in just a second. And then what comes out of the model are the operating cost of delivering that electricity to the load. And another key output that we focus on is renewable curtailment. So in the spring, for example, when there's a lot of solar on the grid, but people aren't using their ACs yet, we end up having more solar than we can use. And we end up having to tell producers of solar energy to turn down their power plants. So that's what curtailment means. And if we can reduce curtailment, that means we're better utilizing our resources. Okay, so this charging flexibility step is a key step that we had to develop in order to get our EVs represented in the model and get this flexibility in here. So if you are charging a vehicle, here on our y-axis we have the cumulative energy that is delivered to an individual vehicle, and on the x-axis we have the time of day. And if you go and you plug in your vehicle and start charging, you're delivering energy, and then the battery's full and you're no longer delivering energy. And this right here, this point right here, might be when you would depart. Because of that, you could delay the onset of the charging to the last possible moment and follow this blue trajectory, and you could still deliver the same amount of energy. So we're assuming that we always deliver as much energy as was delivered in the sort of base run, but we're assuming that anything inside this trapezoid that's monotonically increasing is fair game for a designed trajectory, right? An optimal trajectory. And it turns out that this represents a constraint or a boundary, and you can sum up the boundary across all the individuals and develop an aggregate boundary. This is called the virtual battery model. This is an aggregate boundary on the one side and on the other side, and any monotonically increasing trajectory within here for the full aggregation allows you to deliver the required energy to the fleet of EVs, but choose when it's going to be delivered. So we take those aggregated constraints and we just scale them to geographically represent the state of California, and we scale them into the future to represent the 2025 projection of EV adoption. And then we run them through Flexos. So Flexos is it solves the economic dispatch of generation and storage to serve demand. So you tell Flexos what all the generators are in the electric system and how much they cost to run. And then it has an understanding of the constraints of the transmission from one region to another. And it uses a mixed integer programming solver with a DC power flow model in order to minimize the cost of serving the electricity to all of that demand. So this model is of the entire Western interconnect, so it's the western half of the United States, but we only added our flexible EV load onto the California state. So we focused on California. And we're using the California state projection for what the grid might look like in about 10 years when they achieve the 50% renewable portfolio standard, so where 50% of our electricity will come from renewable sources. So we're talking about high penetrations of renewables. And then we have 3 strategies for our charging. So we have the unmanaged strategy. That would be following that red trajectory in the plot I showed earlier, where the vehicles begin charging as soon as you plug them in. We have the smart scenario where we are optimizing when they charge. And then we have a time of use scenario, which basically means that we provide a price signal to everybody through their electricity rate schedule that incentivizes people to just program their EVs to start charging in the middle of the night. And this is, people really do this. People are already on these rate schedules in PG&E territory. It's going to become the norm for everyone soon. And so we wanted to see how that compared. Okay, so here's an example of some results for some prototypical months. So here we have January, May, and July, and up here we have load on the entire electric system. And this basically just shows that the peak occurs in the evening across the board. And down here is the load from the EVs, and the red line is the unmanaged load. And you can see that when you don't manage the load of the vehicles, their peak coincides with the grid peak. That means that most of the electricity you're providing comes at the most expensive time of the day. So if you enable smart charging, you end up with the blue trajectories, and you can see that across the board, the light blue trajectory shifts the load out of the evening into the middle of the day as well as into the later evening. And then the dark blue is the time of use rate, where we actually just shift all of our load essentially to start in the middle of the night. And then this last graph on the bottom shows renewable curtailment. Renewable curtailment right now is only a major problem in the spring. So here it's happening in the middle of the day because solar is getting wasted. And when we use smart charging, we make an impact on the renewable curtailment. We're not, we're mitigating it to some extent. Okay, so here are what the bottom line results when we think about this on an annual basis. We're getting cost savings by deploying smart charging or this time of use rate schedule approach. And the cost savings are in the range of 35 to 50% of just the cost of providing load to the unmanaged EVs. So you have unmanaged EVs, it costs something to give them electricity, you do smart charging, and all of a sudden it costs half as much to give them that electricity. What's interesting though, I guess the first thing I should note is that these dollar amounts here correspond to the amount of value we are getting by doing this per vehicle per year. And so it ranges from like $60 to $140. So that's actually probably the most important result, which is it's kind of small potatoes. And that's fine. It took a lot of work to get this, but I think that it's important for us to be realistic about whether that's enough value for people to allow a third-party entity to essentially manage the timing of the charging of their vehicle. Is that going to go mainstream? I'm skeptical. That said, the time of use gives you almost as much value as the smart charging, but the time of use is actually a much simpler program. Like once you program your EV to prefer charging in the middle of the night, you just do it once and you forget about it. It's like setting your thermostat. So we can do this for relatively low cost, and we might even get higher adoption of that approach. What's interesting though, this is something that surprised us, is that on the curtailment side, smart charging reduces curtailment because we're shifting some of the load into the middle of the day, but time of use actually increases curtailment because we're pulling load out of the middle of the day and putting it in the nighttime. So I'm going to skip that result and just come to my summary. So what we've accomplished is coupling this PEV mobility and charging model with a production cost grid model, and we've used it to estimate the value of smart charging based on the operational cost of the future California grid. And I should note that what we haven't done yet is to think about what is the cost of implementing these kinds of approaches. It's a little bit harder to do because when we're talking again about managing the charging of people's batteries, you're really talking about people's preferences and their behaviors and how much they're willing to give up in order to extract some value. So the key takeaways are that EV models benefit from being spatially explicit with constrained charging infrastructure and empirical behavioral models, and that smart charging can reduce the cost of serving EVs by up to 50%. Time of use rate schedules can achieve similar cost reductions, but they don't give us the benefits in terms of supporting renewable adoption or renewable rollout. So that's it. Thank you, and any questions?
That was really interesting. I have one question about the operation burden on the energy grid when the PEV case is smart, so that the variance of the demand could be actually increased when it's smart compared to the time of use. Does the operation cost increase just because people are behaving more stochastically with the smart case scenario?
Because we were modeling at a very aggregate scale, we weren't resolving down to the sort of micro variations. This was on an hour by hour scale, how much energy is demanded and supplied. So, but I would say that EVs, this new EV load, represents something like less than, and even for our most aggressive case where we have 5 million EVs, right, that's 20% of all vehicles on the road being EVs. We're still talking, 5% of the electricity load. So it's still a relatively small part of the load. And so even if it's doing new things and moving around a lot, the grid can handle that. It's designed for all kinds of fluctuations.
Yeah, you had a graph that compared the peak loads for the abundance assumption and the constraint assumption, but it looked like the peak was actually the same. Can you introduce constraints that would even it out so that the peak would actually be lower in the constraint case?
Well, that is exactly what would happen. So if I were to show, so that sort of peak that you're referring to in the constrained situation looks something like this. And so when we do smart charging, we actually reduce the size of the peak and we shift when it happens. And that's actually the more important part, is that what we don't want is this peak to line up with that peak. So even if this peak were the same size, but it lined up over here, it would be a lot cheaper to provide that power. Because you can think about this as sort of the line where we have baseload cheap power, and then this is where we have expensive peaker plants running on the grid. So the cost of providing electricity is time varying and depends on where you are in the peak.
I may have missed it, but presumably the range and the charging rates are going to be increasing over time. Is that something that I missed, or did you not?
No, that's a great point. So we did account for it in a relatively unsophisticated way. We said, well, we're dealing with essentially a 10-year projection, so we bumped up the size of the batteries by about 50%. We, in more subsequent work, have now been exploring with, okay, and now what happens if we add charging infrastructure, this much, that much. That's ongoing work right now.
Meaning that the charging infrastructure is better, it can charge faster?
Both. So we're exploring, changing the types of chargers, how fast they charge. There's a diversity, but also the amount of chargers. Because again, you keep adding them and people will use them because now all of a sudden there's one there where they need it.
All right, well, I think that is the end of this presentation. Let's give Colin one more round of applause. And let's give